Well, let's just check then. So we've got cos of 60 degrees is equal to 11 over x. Now, yeah, can I just, one thing, I wouldn't recommend you do this normally. Can I just get you all with your calculator? Could you, remember I said, well, you asked, what is cos? What is the operation? And I said, it's just a number. All right? Could you convert it into that number? I think you might want to do that.
Yeah, x or 11.
I don't know, this is an example of Greg Davis. 11 over x. Alright. Could you just convert the cosine of 60 degrees into the number that it is for me on your calculator? Do you all know how to do that?
Yes.
0.5. So we've got 0.5 equals 11 over x. Right, now, we don't necessarily need to do it this way, but I just want you to understand the link between the work that you've done on fractions and things. What's another way of writing 0.5? A half. So we've actually got 1/2 is 11 over x. So now I could say straight away x is 22. I don't actually need to do any rearranging or calculations or that kind of thing. So just to show you actually that cos of 60 is just a number. And cos of 60 is a nice number because it's a nice fraction, but they're not all like that. So for instance, if I said to you sine of 43 degrees is 5 over x, could we apply the same method to this? So what is sine of 43?
0.6889.
0.6119983 and so on equals 5 over x. So this we're assuming at the moment looks like a what kind of number?
Rational.
Irrational. Oh, sorry, I didn't hear the ear bit. Right. Irrational number. If it's an irrational number, it means we can't do what?
Fraction.
Turn it into a fraction, so we can't do that bit to compare the fractions. But it is just a number. All right. And we can get close to that using a ratio, but maybe not exact, right? That does lead me to something, which is 5 is a length, yeah, of a triangle, an exact length. X will be the exact length of the triangle, yeah? Right? How can then the answer be a non-terminating decimal that goes on forever if we've got an exact length of the triangle? So for instance, if I ask you to work out x now, how would we do it? We would say x equals
Sine
5 divided by sine 43. What is it? Exactly?
So basically, no, it's 9, 3, 3, 1, 3, 9, 5, 9, 2, 3.
And how does that work if x is actually the length of a triangle, side of a triangle?
A triangle side doesn't have to be.
It doesn't have to be whole, but it has to be a finite length, right?
Yeah.
Therefore, surely we ought to be able to write the end of the number somewhere.
Yeah. Yes.
It's not a diagonal triple.
Notice it's not a whole number, you're right there. But it's just something interesting. Why do we have a non-terminating decimal to represent a length that is finite?
I don't know.
Not going to just go on, have a go.
Maybe because there's something that doesn't make the judgment based more and more that we can.
But it has to stop somewhere, I guess, isn't it?
We don't know if it does.
This later on in life you'll come up with, and we have talked about it, the concept of limits and things, and maths has that in there. But we can represent a finite length with an infinite number of things. So, but just not really an issue at this stage in maths, but just something for you because you're all relatively smart, something to consider so that you can have this discussion later on in life. But if we need to find the x, so that was Greg, you said that was the issue when you had the x as the denominator, you said, but you figured it out, yeah?
Yeah.
What did you, when you were struggling, what were you thinking? What were you struggling with? What aspects of it?
Like, initially, I was just clueless, and then I remembered that you had to get x alone, and then another problem came up. I didn't know, like, if the x was on the bottom, if you're supposed to divide or multiply,
Okay.
and then I figured that out
So what was your reasoning for figuring it out, just for everyone else around?
on the internet.
What did it say?
Well, it didn't actually say it explicitly, but I looked at examples, and
Yeah.
for one example, when x was the new denominator, they divided it, and when x was the numerator, they multiplied.
Yeah. Can we come up with maybe some actual reasoning behind it? Has anyone
Yeah.
got it? Yeah, go on.
Well, I was just thinking, if the known number is, like, if you're just thinking about a fraction, how you multiply, how you make it, I don't know how to.
Well, what I would say for everyone is think of it not as a thing, an x, you're looking at just x. Just think of it as a series of things that have been done, and x is purely one of those. And you want to write it in alternative form such that x is the thing that can be worked out. So for instance, I would say, well, this is why I think it's important to say sine of 43 is just a number, because I can rewrite it as using the same thing, a equals b divided by c, yeah? That's all we have. So another example of that would be 4 equals 8 divided by 2. Alright? Now I can write, using the same numbers, I can write other statements that are true, which is?
4 equals,
Well,
oh no.
2 times 4 equals 8. Yeah? Or 8 divided by 4. Alright, so I can write those statements. And what I do, well, if I've got 8 divided by 2 equals 4, well, what do I get if I don't divide by 2? Well, the other side has to equal 8 as well, doesn't it? So if I undo it by timesing by 2, I have to do the same to the other side. It's another way of thinking about it. Okay? But it's quite a nice technique if you've got hard numbers and hard algebra to simplify it to basic levels. Like, you were introduced to this kind of stuff back in P2 or whatever. You know, 8 divided by 2 is 4. Can you write other statements? And that's the reason, because when we get to this stage, we use the same maths. Numbers are just a little bit different. That's all. Right, any other problems you solved?
Yeah. With 2c, it was, you had to find the angle. You had to find
Okay.
the angle was, so, yeah,
So what's the question?
it was, you want to know, like, the triangle was? What it was
So
like?
2c, we think it's...
I believe it is 49.9 degrees.
yeah.
For
So there's the triangle, that's 10, that's the angle we're looking for, and this is 11.9. So we're just trying to find the angle, so,
Opposite over there. I ran into a problem here
yeah,
because I knew that like you had to do inverse tangent at some time,
Yeah.
at some point. I couldn't figure out when, so I looked it up online and I figured out you have to do you have to kind of do the expression like 11.9 over 10. You have to do that first.
yeah, so we're using the right ratio to start with. The right ratio is which one?
Opposite over adjacent.
Opposite over adjacent. So this one's the adjacent side, this one's the opposite side. So we've got TOA, because we're not using the hypotenuse, that one, no, we're not using that. So we've got the tangent of the angle is found by doing 11.9 divided by 10.
Which is 1.19.
which you can, yeah, you can, that's a nice and easy one, which is 1.19. You don't have to do that, and if that turns into a decimal that needs to be rounded, we don't do that. Now, here is an interesting, just to check you understand, that number is a ratio. 1.19 is the ratio between the sides. A triangle, however large it is, where the ratio of the opposite and the adjacent is 1.19, will have the same angle. Okay? And we've got to refer to that angle. So that ratio, 1.19, refers to a specific angle. And we just need to find out what that angle is. So remember I said in the past, that was done by a book. I would go in and I would look for the ratio 1.19 and look at where the angle is, but in your calculators it's done by doing what?
Oh, inverse tan.
The inverse tan. So if I want to find an angle, that's when I'm doing the inverse tan, sine, cosine, that kind of thing. Right? So if you do that and you've got your calculator set to degree modes, you'll get an answer of, what was it?
49.9 degrees.
Okay. Yeah. E3. Okay. Straight to 3D.
Yeah.
All right. So 3D.
Oh no. Oh, I was looking at one end.
What was difficult about 3D?
Well, just if there are two angles on one side, you need to find two other sides.
Okay, so think about this. It says find all missing sides and angles. All right.
Well, you know the other angle.
Yes, you do. How?
Because 24 plus 90 is 114, and then you subtract that from 180.
Okay, and then we do 180 minus 114, which equals 66. Okay, so we've got 66. An easy way would have been those two add up to 90, but it's, we know that, so, but no problem. All right, so we've got all the angles. Now, this is actually an interesting one because let's say I do x and y for the other side. All right, this is a nice example where we've got multiple options. So, for instance, I've got an angle, I've got two angles. I only know one side. I've got to use trigonometry to start with. So I'm going to do SOHCAHTOA. If I write out my theta opposite, oh, it's that hole. This is why I stopped using it. Does yours do this? No? Maybe it's doing the video. Right. It's amazing how actually having too much information can confuse people as well. Right? So what did we say? That was 24, this is 66. Right. This was x. So let's say I want to work out x. What's theta?
Theta?
That's the angle.
And it's 3.66.
You could choose 24 or 66. Don't choose the 90. Why?
Because then the opposite is the same as the hypotenuse.
Yeah. So the 90 is what sets it as a right angle triangle. That's what we're using. We've got to use one of the other two angles. I've seen it before. We need that hypotenuse. But yeah, I can choose 24 or 66. It shouldn't matter. I should get the right one. Which one do you want to choose?
24.
24 I heard first. Okay? But that sets whether x is the opposite or the adjacent. So, the opposite is y, the adjacent is x, the hypotenuse is 14. Now, so that determines which one I use as to which one I want to work out. So I want to work out x first, the y. So I'm going to cross out the y because that's not part of my calculation. So I'm going to use there's nothing with an O. Okay, so we've got the cosine of 24 equals
X over 14.
x over 14. So how do I find x?
You make X 11. So it would be
Yeah,
14 times
Good.
24.
14 times
Cosine
cosine of
24.
24. Can I just, one thing, just to make you aware, I'm not saying you are going to do this, but one of my M3 students, for some reason, when they got to this stage, started swapping the 14 with the 24 and all that kind of thing. Okay? The numbers just started moving around. And I don't know where she got it. It must have been something I'd done or said to her, but we sorted it out. But do you understand that cos of the angle is a thing? It's a number. You can't just swap the numbers around. 14 is the length of the side. Cos of the angle. That's why I said to you, make sure you say it correctly, cos of the angle. It will help you remember. Why would I change to cos of the hypotenuse? It makes no sense. Okay? So just let you know. What did you get? X equals?
1.79.
So 12.8. Okay, so let's put that in my diagram. Like that. Right, right, here's the option. What can I do now? What are my options?
You could use angle 66 as theta, and then you could.
I could.
From then you could do. You could use tangent. You can use all of them at this point. You just
Exactly.
depend on-
Yeah, we heard you. Just say.
But what you shouldn't do.
But you don't need to change to the other angle. You could, if you wanted to stick with cosine. I could keep the same angle but use sine. Okay? Or I could use tangent because I now know the adjacent. I wanted to know that with it. Okay? I could use, as Nick said, I could use Pythagorean theorem because I know two sides to find that. I've got all these options. Which one should you choose?
Whichever one you want. Whichever one
Not tangent. Because
Why?
it's a rounded number.
Okay, that's a good point. Tayson, what are you going to say?
Well, I was going to say sine because that was an angle you used before. But I guess it was
Yeah, there's no issue with that. I would say there is a piece of advice, definitely not a rule, you can use it. I like what Greg said, that x that we calculated is 12.8, we've actually rounded that. Okay? So if we were going to really stick to it, but actually the amount we've rounded it probably won't affect the final answer, but I do like the idea that you said, don't use the rounded answer, use the ones you were, and this is the thing, use the ones you were given. Now there's another reason for use the ones that you were given, which is?
If you made a mistake on the other one.
Exactly. If you made a mistake working out x, then your mistake is going to follow through to y. Now, as a marker, as an examiner, I would be marking it going, well, I know you made a mistake, I will follow that through. If you still use the correct method, I should still give you the marks. However, you might get someone who doesn't pick that up and just goes, wrong, wrong, yeah, move on. All right, if they're not doing it properly. Whereas if you got the first one wrong and then you kind of go, well, I'm going to use the option where I'm not using my answer, I'm going to use the information they were given, then you're kind of just eliminating that little bit of risk. Okay? Does that make sense? Without working out why, do you want us to actually work it out? Should we see the difference between what happens if you do trigonometry and Pythagoras' theorem?
5.6.
So we've got 14 squared should equal 12.8 squared plus y squared. So we've got 14 squared minus 12.8 squared square rooted equals y. Or I would be saying it's sine of 24 is equal to y over 14. So I've got 14 times sine of 24 equals y. But what are those two answers? Are they exactly the same?
The trigonometry one is 5.69, but the 5.7.
Yeah.
And what's this one?
5.715.
Well, is it exactly 6 9?
Yeah, I think it's exactly 6 something. I mean, 5.6 something.
What about the Pythagorean? Can you work that one out for me, just to check it's the same? Or has one method introduced a little bit more error into our calculations?
Probably it's a Pythagorean.
Work it out, if you worked it out.
I got it.
You first, what's it?
Well, I got 5.75.
For Pythagoras' theorem?
I got 5.69.
I didn't round my AC. My X. I round.
Oh, okay, so because you didn't round,
Yeah,
or you did,
I rounded it, but like I rounded it later.
okay. So you've got 5.715,
1.5.
and this was 5.69 something, yeah?
I got 5.67.
For this,
Yeah.
or for this one?
For the square root.
Yeah.
Did you use the 12.8? Yeah, 'cause I think as Ethan was saying, he rounded earlier. Oh no, rounded later. We rounded earlier, so his answer is slightly maybe more accurate. But you can see there is a slight difference in the method, and that's where rounding can be affected by different processes. That if we're squaring, that amplifies the error, doesn't it? You square the answer, you square the error as well.
Oh.
Round to the nearest because those are just two answers.
Well, the idea is with roundings, it's a very interesting point. When you round, if you, well, you should always, how many of you reread the question and say, oh, now I've got to round to 1 decimal place afterwards, or 3 something figures, or who forgets to read that and doesn't do it quite often? The question, what we should always do is if you look at the final accuracy that is required, you should always work at least one level of accuracy higher than that, and never round it to less than that before you get to the final answer. All right? So if I need it to 1 decimal place, I should always work to 2 decimal places all the way through. Okay? That's a good way of it. All right? Okay, so that's all right then, yeah? Any issues with? No? Okay, just a little bit of practice then. On page 258, could you just do question 2 really quickly for me? So convert those into the angles.
And break down the question.
Yeah. Write it down. Sine of A equals 0.467. What is the angle that goes with that? Just a little bit of practice, that's all. It's not meant to be hard because you're using the calculator.